In 1960, in a secure facility somewhere in America, engineers achieved something extraordinary. They built a nuclear reactor small enough to fit in a compact car that could power a spacecraft for years in the depths of space. The SNAP-2 reactor reached full operational capacity, 5 kilowatts of electrical power, enough to run sophisticated instruments far beyond the reach of the sun's light. It passed every ground test. It worked. But here's the thing nobody talks about. SNAP-2 never flew. Not because it failed, but because it succeeded, and in doing so, became trapped by the very forces that created it. This is the story of the nuclear reactor that could have changed everything, and the engineers who watched their masterpiece vanish into the shadows of history. To understand why SNAP-2 mattered, you need to understand the power problem that haunted every space engineer in the late 1950s. Picture yourself trying to design a mission to Jupiter. You've solved the rocket equation, you've figured out the trajectory. But then comes the question that kills dreams. How do you power your spacecraft for the 5-year journey? Solar panels? They're pathetically inadequate once you venture beyond the inner solar system, where sunlight dims exponentially with every mile traveled. Chemical batteries? They offer even worse prospects, degrading within months and adding crushing weight for minimal output. The mathematics were brutal and unforgiving. This was the impossible problem that landed on Harold Finger's desk. As director of the SNAP program, Systems for Nuclear Auxiliary Power, at the Atomic Energy Commission, Finger carried the weight of America's deep space ambitions on his shoulders. He understood what most people couldn't grasp. Without a revolutionary power source, humanity's reach would forever stop at Mars. Everything beyond, the gas giants, the outer solar system, the vast darkness between worlds, would remain eternally out of reach, not because we couldn't get there, but because we couldn't power anything once we arrived. Finger sat in planning meetings at NASA headquarters in 1959, making his case to skeptical administrators. His vision was audacious, a family of nuclear reactors specifically designed for space, with SNAP-2 targeting 3 to 5 kilowatts for satellite and deep space applications. The multi-kilowatt power sources would operate for years, maybe decades, in the harshest environment imaginable. But every time he presented his plans, he faced the same visceral pushback. You want to launch a nuclear reactor on a rocket? What if it explodes during launch? The specter of a radioactive disaster, debris raining down on populated areas, haunted every conversation. One accident, just one, could doom nuclear space power forever and turn public opinion into an insurmountable wall. Yet Finger had something more powerful than optimism. He had necessity on his side, and he had the Cold War. Rumors filtered through intelligence channels that the Soviet Union was developing their own space nuclear program. The space race, already fierce, now extended into power systems. Whoever solved the deep space power problem first would own the future of space exploration. The stakes couldn't be higher, and Finger knew it. America needed SNAP-2 to work, not just for scientific prestige, but for strategic dominance in the new frontier. But having a vision and building the machine are separated by an ocean of engineering nightmares. That's where the real story begins. In the hands of the engineers who had to transform Finger's dream into spinning atoms and flowing electrons. The SNAP-2 reactor that emerged from Atomics International was unlike anything built before. Previous nuclear reactors were massive installations, housed in concrete bunkers with cooling towers reaching toward the sky. SNAP-2 had to be different, compact enough to launch, light enough to reach orbit, and robust enough to operate in the vacuum of space without any of the safety systems terrestrial reactors took for granted. The engineering team faced constraints that would have seemed impossible just a decade earlier. At the heart of SNAP-2 sat a heterogeneous core design that represented a masterpiece of nuclear engineering. The fuel elements combined uranium with zirconium hydride, creating a material that served double duty. The uranium provided the nuclear fuel, while the zirconium hydride acted as a moderator, slowing down neutrons to sustain the chain reaction. Surrounding this core, beryllium and graphite reflectors bounced escaping neutrons back into the fuel, squeezing every possible reaction from the precious uranium. It was elegant, efficient, and completely unproven for space applications. The real challenge came with heat transfer. Nuclear fission generates tremendous thermal energy. SNAP-2's core would operate at temperatures exceeding 1,000 degrees Fahrenheit. That heat had to be captured, transported, and converted into electricity. The engineering team chose liquid sodium-potassium alloy, known by its chemical symbol, Na-K, as the coolant. This metallic liquid could absorb enormous amounts of heat and flow through the reactor's veins, carrying thermal energy away from the core. But Na-K came with a terrifying downside. It's extraordinarily reactive, exploding on contact with water and burning fiercely in air. Working with NOC meant developing entirely new sealing technologies, new testing protocols, new safety procedures. A single leak during testing could mean catastrophic failure and potentially fatal consequences for the engineers nearby. The team persevered, driven by the knowledge that they were building something unprecedented. The Na-K coolant flowed through primary loops, absorbing heat from the reactor core and carrying it to the conversion system. And here's where SNAP-2 became truly revolutionary. Instead of using turbines or generators with their moving parts and inevitable mechanical failures, the system employed thermoelectric modules. These solid-state devices converted heat directly into electricity through the Seebeck effect. When one side of certain materials is hot and the other cold, electrons flow, creating electrical current. No spinning parts, no wearing components. Just temperature differential and physics. The entire reactor and conversion system massed approximately 950 kilograms, heavy by modern standards but remarkably light for a nuclear power plant, capable of generating kilowatts for years. Every component had been scrutinized, optimized, and tested to the breaking point. The engineers had created something that existed at the bleeding edge of what physics and materials science would allow. But building a nuclear reactor for space meant solving a problem that terrestrial power plants never faced: radiation shielding in a mass-constrained environment. The reactor core emitted intense neutron radiation and gamma rays, enough to destroy unshielded electronics in minutes and deliver lethal doses to humans in hours. On Earth, you solve this problem with mass, thick concrete walls, water pools, distance. In space, every kilogram is precious, bought with rocket fuel and engineering compromises. The SNAP-2 team needed a shield that could protect spacecraft systems and potential crew without making the entire package too heavy to launch. The solution came in the form of lithium hydride, a remarkable material that seemed almost designed for this exact purpose. The hydrogen atoms in lithium hydride are extraordinarily effective at slowing down fast neutrons through successive collisions, like trying to stop a bullet by shooting ping-pong balls at it, except the ping-pong balls actually work because of quantum mechanics. Once the neutrons are slowed, the lithium atoms capture them, removing them from the radiation field. And crucially, lithium hydride is remarkably lightweight compared to traditional shielding materials like lead or tungsten. The shield design itself was ingenious in its simplicity: a truncated cone positioned between the reactor and the spacecraft above it. This shadow shield concept meant only protecting what sat in the shadow of the reactor, allowing radiation to escape harmlessly into space below. The geometry was carefully calculated, too small, and the spacecraft would be exposed to dangerous radiation levels; too large, and the mass penalty would be prohibitive. The final design struck a delicate balance, providing adequate protection while keeping the total system within launch constraints. But lithium hydride brought its own challenges. The material is hygroscopic, meaning it absorbs moisture from the air like a sponge. Any water contamination could compromise the shield's effectiveness, creating gaps in protection that would only become apparent during operation. The engineers developed hermetic sealing systems, encasing the lithium hydride in impermeable containers that could withstand the thermal cycling and mechanical stresses of launch and space operation. Every seal, every joint became a potential failure point that had to be tested and validated. Harold Finger found himself fighting a new kind of battle, not against physics, but against politics. In classified briefings with NASA administrators and Air Force generals, he had to walk an impossible tightrope, acknowledge the genuine dangers of nuclear power in space, but demonstrate that the engineering solutions were sound, show confidence without appearing reckless, admit uncertainties without undermining the program. His credibility and the entire future of nuclear power in space hung on these presentations. The ultimate test came in the early 1960s, when SNAP-2 moved from design to reality. Years of work, over $100 million in funding, approximately $900 million in today's money, countless sleepless nights and solved crises, all converged on a series of ground tests that would determine whether the reactor could deliver on its promises. The reactor achieved criticality smoothly, with control rods providing precise power regulation. Watching the instrumentation as the neutron flux climbed, the engineers saw their calculations transform into reality. The thermal systems performed flawlessly. NAK, coolant circulated at design temperatures. Heat rejection systems maintained proper temperature gradients across the thermoelectric modules. And then came the moment that validated everything. The thermoelectric modules generated 5 kilowatts of electrical power. 5 kilowatts sustained, steady, reliable. Enough to run a small household, or, more importantly, enough to power sophisticated spacecraft systems for years in deep space. Extended duration testing pushed the reactor through simulated multi-year mission profiles. The reactor operated for thousands of hours in vacuum chambers that mimicked the space environment. No air for convection cooling, only thermal radiation to shed waste heat. Every test brought new data, new confidence, new validation that SNAP-2 was ready. The engineers had done it. They had built a nuclear reactor that could power humanity's expansion into deep space. But success became a prison. The moment SNAP-2 proved it worked, something unexpected happened. Security classifications tightened dramatically. The Atomic Energy Commission and Department of Defense began classifying virtually every technical detail: reactor specifications, fuel composition, conversion efficiency, test results, even photographs of the facility. The entire design file disappeared behind classification walls. NASA engineers who might integrate SNAP-2 into actual missions couldn't access the data they needed. Test videos that could have demonstrated the technology's viability to mission planners were locked away. Failure analysis that could have improved future designs became inaccessible. Fuel specifications, thermoelectric converter data, operational parameters, all classified. The paranoid logic of the Cold War had created an absurd situation. SNAP-2 was too successful to share. The very capabilities that made it valuable for American space missions also made it sensitive information that couldn't be released. The reactor that was supposed to power America's expansion into space instead became a secret that couldn't be told, a solution that couldn't be implemented, a masterpiece that couldn't be displayed. Harold Finger sat in increasingly tense meetings at AEC headquarters in 1965 and 1966, watching his life's work being slowly suffocated. The antagonistic forces were no longer technical. They were political, bureaucratic, and economic. Mission requirements were shifting. The rapid evolution of solar panel technology, while still inadequate for deep space, was improving faster than anyone had predicted. More advanced nuclear designs were being proposed, including derivatives of SNAP-8 that promised higher power output. And, crucially, the specific missions that SNAP-2 had been designed to power were being canceled or redesigned. The tragic irony was complete. SNAP-2 had demonstrated that the technology was viable. The reactor worked. It generated its target power output. It operated reliably under simulated space conditions. But, by the time it was ready, the world had moved on. More advanced systems were available, mission planners were designing around different power requirements, and the classified nature of SNAP-2's success meant that the broader space community couldn't learn from it, couldn't build on it, couldn't integrate its lessons into future designs. The engineers who had devoted years of their lives to SNAP-2 watched their creation become obsolete, not through failure, but through bureaucratic entropy. The reactor that was supposed to fly to Jupiter, to Saturn, to the outer darkness of the solar system, never left Earth. It sat in its test facility, a fully functional nuclear power plant designed for space, going nowhere. Eventually, the program was terminated. The hardware was either dismantled or disappeared into storage. The documentation remained classified. The knowledge, hard-won through years of engineering challenges, scattered as the team moved on to other projects. Looking back across the decades, SNAP-2 stands as a monument to both human ingenuity and institutional dysfunction. The engineers solved problems that had never been solved before. They created materials science innovations, developed new testing protocols, pushed the boundaries of nuclear engineering and space systems integration. The heterogeneous uranium-zirconium hydride fuel design, the NAK cooling system, the thermoelectric conversion modules, the lithium hydride shadow shield, each represented a triumph of engineering over seemingly impossible constraints. The reactor's 5 kilowatt output might seem modest by modern standards, but in 1960, it represented a revolution. 5 kilowatts sustained for years, in the vacuum of space, from a package massing less than a ton. That power density, that reliability, that longevity, these were the keys to deep space exploration. With SNAP-2, missions to the outer solar system would have been powered by American nuclear technology, carrying instruments that could operate for decades rather than months. But the story of SNAP-2 is ultimately about more than engineering specifications and power outputs. It's about the humans who built it, engineers like Harold Finger, who fought bureaucratic battles to keep the program alive, the unnamed team members at Atomics International who solved the NAK coolant challenges, who designed the shield geometry, who tested and refined the thermoelectric modules. These were people who believed they were building the future, who saw their work as opening the cosmos to human exploration. The secrecy that killed SNAP-2 was born from legitimate concerns. Nuclear technology was sensitive, and the Cold War made every advantage precious. But that secrecy also prevented the cross-pollination of ideas, the sharing of lessons learned, the building of institutional knowledge that drives technological progress. When SNAP-2's design files were classified, when its test results were locked away, when its engineers couldn't publish or share their work, the entire space community lost access to a wealth of knowledge. Future reactor designs had to rediscover solutions that SNAP-2 had already found. Problems that had been solved had to be solved again, wasting time and resources. The 950 kilogram reactor that generated 5 kilowatts of power sits now only in declassified documents and fading memories. The hardware is gone. The facilities have been repurposed or demolished. The engineers have retired or passed away. But the ghost of SNAP-2 haunts every discussion of nuclear power in space. When modern mission planners consider nuclear reactors for Mars bases or deep space probes, they're walking paths that SNAP-2's engineers blazed decades ago. When new reactor designs use uranium hydride fuels, or thermoelectric conversion, or shadow shielding, they're rediscovering solutions that SNAP-2 proved viable in 1960. There's a particular poignancy in success that goes unrecognized. SNAP-2 worked. It achieved its design goals. It demonstrated that nuclear power in space was not just possible, but practical. And then it disappeared, not into the cosmos it was built to explore, but into the classified archives of Cold War secrecy. The reactor that was supposed to power humanity's expansion into deep space instead became a footnote, a might have been, a road not taken. We can only speculate about the alternate history where SNAP-2 flew. Perhaps missions to Jupiter would have launched a decade earlier, powered by reliable nuclear reactors instead of waiting for radioisotope thermoelectric generators. Perhaps the lessons learned from operational space reactors would have accelerated the development of more advanced systems. Perhaps the public would have become more comfortable with nuclear power in space, seeing it as a tool for exploration rather than a threat. Or perhaps the same forces that killed SNAP-2 on the ground would have found other ways to prevent its deployment. What we know for certain is that the engineers who built SNAP-2 achieved something remarkable. In an era when space exploration was in its infancy, when the basic principles of operating in vacuum were still being discovered, they designed and built a nuclear reactor capable of operating for years in the harshest environment imaginable. They solved the heat transfer problem with liquid metal coolants. They converted that heat to electricity with solid-state thermoelectric modules. They shielded the radiation with innovative materials and geometry. They tested their creation through thousands of hours of operation, validating every design decision. And then they watched it die. not with a bang, but with a whimper, strangled by classification and obsolescence. The reactor that could have changed everything instead changed nothing, leaving only the bitter knowledge that it worked, that it was ready, that it could have flown. In the end, SNAP-2's legacy is a warning as much as an inspiration. It reminds us that technological success is necessary, but not sufficient. That secrecy can protect advantages, but also prevent progress. That timing matters as much as capability. That the path from laboratory to deployment is treacherous, filled with obstacles that have nothing to do with engineering and everything to do with politics, bureaucracy, and the chaotic evolution of priorities. The 5 kilowatts that SNAP-2 generated in its test facility represented more than electrical power. They represented human ambition, the drive to push beyond our limitations, the refusal to accept that deep space must remain forever dark and silent. Those kilowatts proved that we could build machines to carry our presence into the cosmos, to power our instruments and our dreams across the vast distances between worlds. That the reactor never flew doesn't diminish what its engineers achieved. They built something that worked, something that was ready, something that could have opened the outer solar system to exploration decades before it actually happened. The fact that institutional forces prevented that deployment is a tragedy, but it doesn't erase the triumph of the engineering itself. SNAP-2 remains a ghost in the machine of space exploration, present in every modern space reactor design, in every discussion of nuclear power beyond Earth, in every mission that ventures into the darkness where sunlight fails. The engineers who built it proved it could be done. They showed us the way, even if we didn't follow their path. And somewhere in declassified archives, the specifications and test results wait, a testament to what was achieved and what might have been. A reminder that sometimes the greatest barrier to reaching the stars isn't the physics of the cosmos, but the politics of Earth. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.